Causal set theory, an alternative theory of spacetime, proposing that it is made up of discrete events ordered by causality. Causal set theory, CST, is an alternative approach to understanding the structure of spacetime, rooted in the idea that spacetime is fundamentally discrete rather than continuous. Unlike general relativity, which models spacetime as a smooth, four-dimensional manifold, CST proposes that spacetime consists of discrete events or points. These events are connected by causal relationships, reflecting the fundamental ordering of cause and effect. This discrete nature aligns with quantum theory, which suggests a minimum scale, Planck length, beyond which the continuum description breaks down. In classical spacetime, you can infinitely zoom into smaller and smaller regions. In CST, zooming in beyond the Planck scale reveals individual events, akin to pixels in a digital image. Think of spacetime as a digital photograph. At a distance, it looks smooth and continuous, but when magnified, the discrete pixels, events, become apparent, each with its own role in the overall image. One of the core motivations for CST is addressing the continuum paradox in classical physics. General relativity treats spacetime as infinitely divisible, leading to problems such as singularities, points of infinite density, and infinities in quantum field theory. CST introduces a minimum scale, the Planck length, ensuring that spacetime is fundamentally discrete. This resolves the issue of infinite divisibility, providing a finite and manageable framework for describing the universe at the smallest scales. In quantum mechanics, particles, like electrons, have discrete energy levels. Similarly, CST posits that spacetime itself has discrete levels or events, avoiding the mathematical inconsistencies of a continuum. It's like switching from a smooth analog clock to a digital one. The digital clock represents time in discrete steps, avoiding the paradoxes of infinite divisibility present in analog time. In CST, causality replaces the traditional notion of spacetime coordinates as the primary structure of the universe. Each event in the causal set has a well-defined position in a causal sequence. It either precedes, follows, or is unrelated to another event. This causal ordering preserves the light cone structure of general relativity, ensuring that events respect the fundamental limits set by the speed of light and causal influence. If event A is the emission of a light pulse and event B is its detection, A causally precedes B. The relationship between A and B defines their positions in the causal set. Causality in CST is like the sequence of dominoes in a chain reaction. Each domino, event, only falls after the previous one impacts it, preserving the order of cause and effect. Lorentz invariance, a cornerstone of relativity, ensures that the laws of physics are the same for all observers, regardless of their relative motion. CST respects Lorentz invariance by maintaining that the causal relationships between events remain unchanged under Lorentz transformations. This means that even though CST deals with discrete events, its predictions align with the continuous spacetime symmetries observed at macroscopic scales. Two observers moving relative to each other may disagree on the time interval between two events, but will always agree on their causal order, which event came first. It's like two people watching the same movie on different screens. They might experience the scenes at slightly different times due to playback differences, but the sequence of scenes remains consistent for both. CST models the dynamic evolution of spacetime through stochastic sequential growth. Events are added one by one to the causal set in a way that preserves causality. This process mimics the unfolding of spacetime, where new events grow on the causal structure of past events. The randomness in the growth process reflects the inherent uncertainty of quantum mechanics while maintaining a coherent causal structure. Imagine a causal set growing from a single event, with each new event causally connected to some subset of previous events. The structure expands while respecting the cause-effect relationships. It's like building a tree, where each new branch grows from an existing node, maintaining the overall shape and structure of the tree. In CST, the geometric properties of spacetime, such as volume and curvature, emerge from the causal relationships between events. The volume of a region of spacetime is determined by counting the number of events within that region. Curvature, which in general relativity is described by the Einstein field equations, corresponds to variations in the density and connectivity of events in the causal set. A flat spacetime region might have a uniformly distributed set of events, while a curved region, like near a massive object, would show a denser clustering of events. It's like using the number of Lego bricks in a specific area to estimate the volume of a structure. The density of the bricks in different regions reflects the curvature or flatness of the space. CST provides a framework for developing a theory of quantum gravity, which seeks to reconcile general relativity with quantum mechanics. By quantizing spacetime itself, CST avoids the infinities that plague quantum field theory on a continuum. This approach allows for a finite, self-consistent model of spacetime that incorporates both gravitational and quantum phenomena. When calculating quantum fields in a causal set, there are no divergences, infinities, because the number of events is finite, providing well-defined results for physical quantities like energy and momentum. Quantum gravity in CST is like simulating water flow using a grid of finite cells. The discrete grid avoids the computational errors that arise when dealing with a continuous system. CST offers a novel perspective on black holes and singularities. In general relativity, singularities represent points of infinite density and curvature. However, in CST, these infinities are avoided because spacetime is made up of discrete events. Instead of a singular point, a black hole's core might consist of a densely packed causal set, smoothing out what would otherwise be an infinite curvature. Near the event horizon of a black hole, CST predicts a dense clustering of events, but no single point of infinite density, potentially resolving the singularity problem. It's like replacing the sharp tip of a needle with a cluster of tiny spheres. The dangerous singularity is softened by the discrete nature of the structure. Testing CST involves searching for observational signatures of spacetime discreteness. These might include deviations from classical predictions in phenomena like gravitational waves, the cosmic microwave background, CMB, or high-energy particle collisions. Since CST predicts slight deviations from continuum models at extremely small scales, future experiments with advanced precision could reveal these effects. Gravitational wave signals might exhibit small periodic fluctuations that reflect the underlying discrete structure of spacetime predicted by CST. Testing CST is like examining a seemingly smooth fabric under a microscope to reveal its weave. At large scales, the fabric appears continuous, but under high magnification, its discrete threads become visible. Causal set theory offers a compelling framework for understanding spacetime as a fundamentally discrete entity. By integrating causality as the primary organizing principle, CST preserves the key features of relativity while addressing the inconsistencies of a continuum model. If validated, CST could revolutionize our understanding of the universe, providing a consistent foundation for both classical and quantum physics. Future advancements in observational technology and theoretical modeling may confirm CST's predictions, leading to breakthroughs in fields such as cosmology and particle physics. Causal set theory is like discovering that what we thought was a smooth ocean surface is actually composed of countless tiny droplets, each playing a role in the larger structure.